Okay, yeah, so I want to talk about analog digital converters today. So let's go ahead and talk about that right now, and then we'll see if there's other questions after that. Um, Engineering 250, digital logic, we're talking about digital circuits, right? So this idea that everything is a 1 or a 0, 5 volts or 0 volts. So we break the world into these binary buckets, and we just nominally call these 0 and 1. And if we build a circuit, typically this means 0 volts or ground, and this means 5 volts or power, or sometimes we'll see the word VCC, which means the same thing. And sometimes this will mean no and yes, off and on, false and true. But these are kind of arbitrary, right? The essential feature is that we've broken things into two buckets, right? A statement can be true or false, a light bulb can be on or off, an answer can be yes or no. And we use 1 and 0, or sometimes, T or F, as kind of our universal designator of these buckets. But this association is kind of arbitrary, right? We could just as easily build a circuit where 1 means off and 0 means on. Okay, and in fact, we'll see this. We'll build circuits where if you put a 0, a ground level, a 0 volts into your circuit, we have a light bulb that turns on. And if you put 1 into your circuit, your light bulb turns off. So this mapping between 0, 1 and these different categories is pretty arbitrary. In fact, there's a version of logic called negative logic where all of these things get reversed, where 0 means true and 1 means false and so on. But usually we'll stick to these conventions, right? But the main thing is we're breaking things into buckets. Okay, well, inside our theoretical world of Engineering 250, that works great. But in the world outside of class, right, things are not just on or off. There's voltage levels, Engineering 120. So if we look at a graph of voltage versus time, we might see a signal that changes like a sine wave. It goes high and low like this. And maybe this is 0 volts, and maybe this is 1 volt. Okay, so it's a sine wave with an amplitude of a peak-to-peak amplitude of 1 volt, and it's centered at 0.5 volts. And maybe we have a computer circuit that wants to do something with this, like analyze it and record it and play it back. Okay, a music player. Well, if our computer only has 1s and 0s, but we have this thing which goes smoothly between 0 volts and 1 volts, how are we going to store this inside our computer? And the answer is we digitize it. And so digitizing is basically the process of taking an analog signal and changing it into a digital form. So we have something called an ADC. This is an analog to digital converter. And so that last question in the homework is talking about ADCs. And if we're not too worried about accuracy, we could do a pretty crude representation of this waveform in terms of 0s and 1s by just picking an arbitrary point, like maybe 0.5 volts, and saying, if our signal is smaller than 0.5, we're going to treat that as a 0. So we have a 0 and a 1. And if it's bigger than 0.5, we're going to treat it as being a 1. And when it gets to be smaller, we're going to treat that as a 0. And when it's bigger, we're going to treat that as a 1. And when it's smaller than 0.5, we're going to treat that as a 0. And, this kind of looks a little bit like this. Not really, but, goes up, goes down, goes up, goes down. It's got the basic idea, right? This is an approximation of this original waveform. This is digital, this is analog. Okay, so a really crude analog to digital converter might take this nice smooth sine wave and change it into this. Okay, we are representing our digitized signal with a single bit, a 0 or a 1. So this is a 1-bit analog to digital converter. Suppose we wanted a more accurate representation. We could make a 2-bit analog to digital converter. So let's look at this. Here's our original signal, and it's a sine wave. And here's time. And let's digitize it. Instead of just using a single bit, let's use 2 bits. So we will have 4 possible voltage levels, right? With 1 bit, we had 2 possible voltage levels. With 2 bits, we have 4 combinations of 2 bits, so we have 1, 2, 3, 4 possibilities. And the easiest way to represent this original signal might be to break it up into 4 regions. So here's 0.25 volts, here's 0.50, here's 0.75, and here's 1. And now what we're going to do is we're going to use 2 bits to represent this voltage level. And we're going to get something like this. And I'm just digitizing our input signal. And I'm basically breaking it into buckets. So all the values between this point in time and this point in time are voltage levels between 0 and 0.25. I'm going to call that a 0. Okay, so 0, 0. I'm going to call this 0 to 0.25. This is going to be 0.25 to 0.5. This is going to be 0.5 to 0.75. This is going to be 0.75 to 1. Alright, so any voltages between 0 and 0.25, I'm going to represent that as 0, 0. But here between 0.25 and 5, that's going to be a 0, 1. 0.5 to 0.75, that's going to be a 1, 0. And anything above 0.75, that's going to be a 1, 1. And so if I do this carefully, my waveform is going to look something like this. I'm amazed I haven't made a mistake yet, but I still got time. Alright. So there's a different digitized version of our original signal. Now our original 1-bit digitizer was pretty crude. It was just on or off. Our 2-bit digitizer, it looks a little more like it's following this, right? It kind of loses it on the curved parts up here. But you know, we've got this idea that it's slowly rising and then starts falling and so on. Okay, this is a 2-bit analog to digital converter. So what you may have already guessed is that the more bits we have, generally the more accurate this picture is going to be. If we were to use 3 bits, we would break this into 8 bins, and now each of these bins would cover 0.125 volts. Okay, so let's just generalize that, and then we've got our solution to question 9. So suppose your input goes from 0 to 1 volt. And suppose you have, let's say, 4 bits. Okay, first question, can somebody tell me, if you have 4 bits, how many things can you represent with 4 bits?
16.
16. How did you get 16?
So 1 bit would be 1, 2 bits would be 2, 3 bits would, oh, wait, would it be 8?
No, you were right. 1 bit is actually 2 things, right? So 1 bit, you have 2 things, right? 0 or 1. 2 bits you have 4, 3 bits you have 8, 4 bits you have 16. In general, if you have n bits, you can represent 2 to the n different things. So any CS majors, when you take CSE 215, discrete structures, we will visit this fact about 20 different times throughout the course in 20 different contexts. But for now, you can just take it on faith or remember from 120. If you have n bits, you can represent 2 to the n different things. Okay, so 4 bits, we have 16 bins, or 16, you know, of these buckets that we can break our input into. Well, if we have 1 volt and we break it into 16 bins, we have 1/16 of a volt per bin. Okay, what does this mean? This is about resolution. Our waveform over here, right, could have been doing something like this. Could have had this little squiggle in here, right? But because every voltage in here was still between 0.5 and 0.75, we still just represent it as a 1, 0. We don't notice those little squiggles. And in general, if a squiggle changes by less than this distance, which is 0.25, we're not going to notice it. So our resolution in this case is 0.25. Okay? We have to have a change bigger than 0.25 to guarantee that we see a change in which bucket that voltage goes into. So in the general case, well, in this case, if we had 4 bits, our resolution would be 1/16, right? Which is 1 over 2 to the 4th. So a pretty small amount. Okay, 0.0625. If we had 10 bits, our resolution would be about 1/1000th, about a millivolt. So 10 bits, you can break things into 2 to the 10th, which is 10 to the 1024. And so your resolution is 1 over 1024, which is about 1 millivolt. So that's pretty good. All right, so the absolute general formula, right, this was all for input range from 0 to 1 volt. So here's the more general case. Input ranges from voltage minimum to voltage maximum, and you have n bits. Then your resolution is the total voltage range you're trying to represent, which is the difference between the max and the min, divided by the number of bins, which is 2 to the n. So that's the formula you'll find in the book for the resolution of an n-bit analog to digital converter if your input ranges between Vmax and Vmin. All right, once you have that, we can look at the solved question, for example. Here's an analog to digital converter. There's the formula. Resolution of least significant bit less than 0.25 volts, full scale, voltage range of 5 volts. Okay, so they're talking about the scale of the voltage range. That's the maximum minus the minimum. And I think in this book, Izad's assuming that your minimum voltage is always ground. So suppose that your input goes from 0 to 0.25 volts. Sorry, 0 to 5 volts. Okay, that's your range. So let's suppose Vmax equals 5 volts, Vmin equals 0 volts. Well, this question is asking you, if you want a resolution of 0.25 volts, how many bits do you need? Okay, this formula says if you have n bits, this is your resolution. But the question is saying if you want a resolution of 0.25 volts, how many bits do you need? Find the minimum number of output bits. Okay, so if we want resolution equals 0.25. That should equal Vmax minus Vmin over 2 to the n. We're told the voltage range in this part A is 5 volts, so Vmax minus Vmin is 5 divided by 2 to the n. So now do the algebra, solve this equation for n. 0.25 equals 5 over 2 to the n. So multiply by 2 to the n. 2 to the n times 0.25 equals 5. Divide by 0.25. 2 to the n is equal to 5 over 0.25. Pull out your calculator. This is equal to 20. So what value of n makes 2 to the n equal to 20? Well, 2 to the 4th is 16. 2 to the 5th is 32. So n is 4 point something. It's bigger than 4. So if we want an A to D converter that has this resolution for this voltage range, we need at least 5 bits. Does that make sense?
I think so. Are you recording this though?
Yes, I am.
Later?
Yeah, so
Okay.
I'll post this later. When you get to Engineering 270, we talk more about analog digital converters, and we go through this in more detail then. Did somebody have their hand up?
I mean, I got a question. Right now, I'm on 6U, doing arithmetic addition,
Mm-hmm.
and such. Yeah, I just don't know how to, like, the total 1 to 3. I was looking at the, like, the solution one. I'm not sure how to take the rights, where to put the 1s and 0s, per se.
So which part are you working on for 6U?
Yeah, on A.
On
Can
A.
I do A?
Let's go ahead and do A. So we're asked to calculate 123 plus negative 125. All right. So first question, can you write 123 in binary?
Are we supposed to, like, find the sums of, like, the 1s and 0s to equal 123?
Exactly, yeah. And you can do it by trial and error. You can start with 64 and then 32 and 16 and so on. But there's this procedure we went through on Tuesday, and let me just run through that again really quickly. 123 divided by 2 is equal to 61 with a remainder of 1. 61 divided by 2 is equal to 30 with a remainder 1. And if I make a mistake here, somebody tell me. Otherwise, we'll all get the wrong answer in the end. So I'm just going to keep taking this quotient, dividing it by 2, writing the integer quotient and the remainder until I end up with 0, remainder 0. So this is just an algorithm. So 1 divided by 2, this one's tricky. It's equal to 0 with a remainder of 1. And then 0 divided by 2 is 0 with a remainder of 0. Okay, and then at that point, use these remainders to write your number. So 0, 1, 1, 1, 1, 0, 1, 1. That's 123 in binary. Alright, so that's the first trick, is just writing these in binary. If you do the same thing and you try to write 125, you'll end up with this. Okay, so you gotta go through the same procedure. And that gives you the number 125. Okay, next step, write negative 125. How do we do that? 2's complement. Okay.
We just flip around the 1s and 0s. Wherever there was a 1, we make it a 0, and then the 0s shrinks into 1s.
Right, so we flip around the 1s and 0s, and then we have to do one more thing. And we have to add 1. and that's going to give us negative 125. All right, so we wrote 123, we wrote 125, we took its 2's complement to get negative 125. The last piece of, well, almost the last piece of this is to do the addition. All right, and addition here, we need to pretend we're adding decimal numbers, and if we get an overflow, we write down the last digit and we carry the first digit. So overflow for binary is 2 or more. So 1 plus 1 is 2, right, which looks like this. So write down that 0, carry the 1. 1 plus 1 plus 1 is 3, which looks like this in binary. So write down that 1, carry the 1 to the next column. 1 plus 0 plus 1 is 1. With no carry, 0 plus 1 plus 0 is 1. With no carry, 0, 1, 0 is 1, and we don't have any carries anywhere in sight. 0 plus 1 plus 0 is 1. With no carry, 0, 0, 1 is 1. So this is 123 plus negative 125. So this is your answer in binary. Okay, it's guaranteed that's what your sum is in binary. But if you want to find your sum in decimal, we have to convert this back into decimal. So you have to check the sign bit. If this sign bit was a 0, we could just add up the powers of 2 and we'd be done. But because this is a 1, we know that this is a negative number. Okay, so let's take the 2's complement to get the positive value of this. Figure out what that is by adding powers of 2, and then we'll just throw a minus sign in front. Okay, so take the 2's complement of this. So 0, 0, 0, 0, 0, 0, 0, 1 plus 1. 1 and 1 is 0, carry the 1. 1 and 0 is 1, and then no carries anywhere. And that's equal to 2. Okay, since this is equal to 2, this is equal to negative 2. And so that's your answer. 123 plus negative 125 is negative 2.
Alright, say like for the fifth step, can we just skip that fifth step and just put negative 2? It's actually negative 2.
If you can convince me when I'm grading that this is equal to negative 2, that's fine. But if you just write this and you say negative 2, you're going to lose points for that.
Okay, alright.
Right, so you're doing this to explain why this is equal to negative 2. And really, you're just doing it to practice, right? I mean, that's the point of these exercises.
Gotcha. Alright, thank you.
Cool, you're welcome. Alright, other questions on homework or lab?
Did we have to do the ones marked with S?
No.
The basic solutions.
So you're only required to write up the ones marked with U, and my general recommendation is ignore the ones with S unless you're really, really badly stuck. And if you're totally stuck and you don't know where to go, take a peek at the S's to try to get a hint. Okay? But just work on the U's, write up the U's to turn in, and don't even look at the S's. Because inevitably people look at the solved problems and then they find what's different between the S and the U and they adjust the solution accordingly, right? And that lets you finish your homework, but it really doesn't teach you what you're trying to learn. So it's really sort of wasting your time because you're writing up the homework, you're getting a few points for the homework, but you're not learning the concepts. So kind of ignore the S problems unless you're totally stuck. And if you're stuck, I would say send me an email or come to office hours first before you turn to the solved problems, right? But if you're hopelessly stuck or, you know, it's due in 5 minutes or something, go ahead and look at the solved versions.
Got it. Thanks.
All right, you're welcome. All right, other questions? So this sort of deals with this question 7, right? Number of bits required to display to uniquely assign a code to this many pieces of art, right? So we're looking at powers of 2, right? If you have n bits, you can represent 2 to the n things with those n bits. So 2 to the 10th is 1024. You need more than 10 bits to represent 2520 art pieces, right? 2 to the 11th is 2048. That's not enough either. 2 to the 12th is 4096. Okay, that's enough. So 12 bits is the minimum number of bits you need to represent 2520 things. You could use more bits. You could use 100 bits, and you've just got extra bits left over, right? But if you only have 5 bits, you can only represent 32 things, no matter how clever your coding scheme is. So that's what this question is asking you. All right, good. So I'll be posting an announcement right after class. The Zoom code for this class is going to change after today. Okay, and I will post in an announcement on Canvas the new link to get into this classroom. Okay, so this classroom I'm going to close after this week, and you'll have to use the new code to get in. Okay, so that'll be posted on Canvas in the announcement, so make sure you look there. And as usual, if anything goes wrong, you can't get in, shoot an email to me, and I'll try to help you like that. But new meeting code, because I've been asked to make sure that classes have different codes, so so just pay attention to that. All right, so let's continue digging into digital logic. And again, a lot of this is going to be review. Okay, a lot of what we're doing in here is stuff that you've already done in 120. But as we're reviewing, we're periodically going to jump off into a different direction. And when I was in school, I always got in trouble for this, because I would come to the lecture, I'd sit down, the teacher would start talking about something that I already knew, and I would zone out. And I would, be doing something else, and then next time I looked at the board, I had no idea what we were talking about. Okay, so that's going to happen a fair amount in this course, this business of starting with something we've already talked about, and then going in a different direction. So I'll ask you to be patient if this seems like review, and stay tuned in so that when we start expanding on this, you know that there's new stuff happening. Today's will largely be review, though. We won't do a whole lot of branching off, but we'll get into a few new things perhaps. So let's start with the idea of logic. Okay. So we have logic gates, logic operations. So we have things like and, or, not, NAND, NOR, XOR, XNOR. Those are probably the main ones that we've encountered. And these are ways to take binary digits, bits, and combine them to produce new bits. So let's look at a not operator, right? Not is negation, inversion. Very simple operation. If you take a 0, the not of a 0 is 1. And if you take a 1, the not gives you a 0. So it just complements your bit value. That's what we were doing when we took 2's complement. And we can represent this with a logic diagram like this. So we put an x into this inverter, and the complement of x comes out the other side. So if x goes in, this is not x. And we usually write not x as x with a bar on top. Sometimes you'll see it written as a tilde in front of x. Okay, that's because if you're on a typewriter, it's hard to put a bar on top of a letter, so we put a symbol in front of it. But mostly we'll do x with a bar on top. And we can describe the behavior of this gate using a truth table. So a truth table is like a multiplication table. When we learn to multiply as kids, we get a chart and it shows us numbers, and each time that we match two numbers, we find what the product is, right? So we had a multiplication table that went from 12 to 12, and it had 144 entries in it, and if you want to know what 7 times 8 was, you look at 7 and 8, and it would be 56, okay? That works for small numbers, but we can't do that to multiply all possible numbers because there's an infinite number of numbers, right? But in binary, there's only two numbers, 0 and 1. So this kind of multiplication table approach will let us completely explain what an operation does. So we just list them in a straight table. If we have a variable x, it can only have one of two values, 0 or 1. And if it's a 0, the inverse, the not of 0, will be 1, and if it's a 1, the inverse will be 0. So this completely describes what a not operation does, or an inverter. Okay, so that's the truth table. That's the picture of the circuit diagram. This is how we write it in Boolean Algebra. Okay, that's the symbology for it, is x with a bar on top. And this is also called an inverter. And if you're keeping track, right, this was typically a 74 LS04 if we wanted to get an actual part from our parts bin to do inversion. Okay, well, ands and ors and XORs and stuff operate on two or more inputs. So let's just think about two input variables. Let's call our variables x and y. And we've already said a few times, if you have 2 bits, x and y are each a bit, we have 4 possible combinations of those, right? This is how we can represent 4 things. 4 different combinations of these. But if we explain exactly what an AND does for each of these 4 cases, that's all we need to say. We've completely explained what an AND operation does. Okay, so let's make a column for AND. And our AND gate looks like this. And I usually put a little dot inside my AND gates to indicate this is an AND. And we'll see why when we get to an OR. So it takes 2 inputs, x and y. And the output is just x dot y. And sometimes, if it's clear, we leave off the dot and we just write xy. And what an AND does is it outputs a 1 if x is 1 and y is 1. So if both of these inputs are 1, the AND of them is 1, otherwise the AND is 0. And this operation is sometimes called a product. So the product of x and y is the same as x ANDed with y. Alright, we also have an OR gate. And the OR gate looks like an AND, but it has this little curved edge to it. But I put a plus symbol in there also to represent OR. And 2 inputs, x and y, and the output is x plus y. Okay? And it's not addition, it's the logical OR operation. And an OR is 1 if x is 1 or y is 1. So here y is 1, the output's going to be 1. Here x is 1. Here both of them are 1, so you know that's certainly 1. But in this case, x is not 1, y is not 1. The OR output's a 0. Alright, so we can start filling these in now. So a NAND gate, which is a not AND. Think of an AND gate, but put a not after it. So we draw this as an AND gate with a little circle on the end. In logic diagrams, circles like this or this usually mean negation. So x and y go in, and what comes out is xy with a bar on top. And it's just the negation of the AND. So an AND is 0, 0, 0, 1. A NAND is 1, 1, 1, 0. And a NOR is a not OR. So it looks like an OR gate with a little circle on the end. Inputs are x and y. The output is x or y with a bar on top. And it's the negation of the OR column. 0, 1, 1, 1 becomes 1, 0, 0, 0. Alright, and then just to round these out, XOR. This is an exclusive OR. So it looks like an OR gate, but we put an extra bar here in the beginning. And I usually put a plus inside a circle inside that symbol just to make it clear that this is an exclusive OR. And we represent it as x plus circle y. And an XOR works exactly like an OR, except you're not allowed to have both x and y 1. It's got to be x is true or y is true, but not both. So the XOR looks like this. And the XNOR is just the opposite of the XOR. And so you put a little circle on the end out here, or you put a bar over the x plus y. And that gets you your exclusive NOR. There's other logic functions possible, but this gives us a basic set of logic operations, and we can build most of what we want to do in this course just from these few gates. In fact, mostly we'll just use AND/OR and AND/NOR, occasionally XORs and inverters. Alright, we can also have gates with more than 2 inputs. For example, we could do A ANDed with B ANDed with C. And this might look like this. So 3 inputs going in and output X, and X is equal to ABC. And we can write the truth table for that. But now we have 3 inputs. We have 8 possible combinations of those inputs, 8 being 2 to the 3rd. And a 3-input AND gate says all the inputs have to be 1. So here A and B and C are all 1, the output's 1. But in all these other 7 cases, at least one input fails to be 1, so these all output a 0. And when I start drawing truth tables with more than 4 rows, I usually break it up into chunks of 4, just to make it a little easier to read. So there's a 3-input AND gate. Here's a 3-input OR gate. Right, and as long as at least one input, possibly more, is 1, the output of the OR gate will be 1. And that, you know, you can imagine how to draw it. Looks like that. Alright, so we have truth tables, we have Boolean equations, we have symbolic representations of these logic gates, and these all go together. Okay. So, what do we do with this? Let's talk a little bit about facts of Boolean algebra, and then we'll talk about how we actually design circuits and write truth tables to get some kind of behavior. Okay, and this should end up being all that you need to do experiment 4 on lab 1. If you haven't already done that, we'll be going over that in a few minutes. But let's talk a little more about Boolean algebra first before we start moving to circuits. So in 120 we usually talk somewhat about these rules of Boolean algebra, these things that we can do. For example, it turns out that, so assume that everything that I'm going to write here is a Boolean variable, A, B, C, and so on. It turns out if A and B are Boolean variables, and we take A and B, we get exactly the same thing as B ANDed with A, right? Why is that? Because, you know, 1 ANDed with 1 is a 1, right? 1 ANDed with 1 is a 1. Well, 1, 0 is a 0. 0, 1 is also a 0, right? The order of x and y doesn't matter. So A ANDed with B equals B ANDed with A. And it turns out that if we do an OR, the order doesn't matter there either. Okay. Anybody know what these are called? What property this is named? So this is the commutative property. And we say that ands and ors are commutative. So you can change the order of these operations. It also turns out the order in which we group things together does not matter. For example, if we want to take A and AND it with B, C, we can also take A, AND it with B, and then take that result and AND it with C. So if we just write something like A, B, C, it's unambiguous. It doesn't matter if we AND these first and then AND the result with C, or we AND B with C and then AND A with that result. Okay, so this is a property called being associative. If we take a bit and we negate it twice, we end up with just the original bit. That's something called double negation. Right? So negating 0 gives you 1, negating it again gives you 0. We can distribute, just like we do in regular algebra. If we take B or C and we AND that with A, that's the same thing as A ANDed with B or A ANDed with C. And there's another form of that. We could do A or BC equals A or B ANDed with A or C. So this is distribution. And in your text, you can find a whole bunch of these things. I'm not going to go through all of them, but I want to just give you kind of a flavor of what some of these things are and what they mean. There are ways that we can manipulate equations involving binary variables into other equations. And this is useful because these equations are eventually going to turn into circuits. Okay? But if we had a circuit equation like this, that would turn into an AND gate, an AND gate, and an OR gate. That's 3 gates. If we knew that that was equivalent to this, we could build this with only 2 gates, an AND gate and an OR gate. So this is going to be simpler to build. Fewer wires, fewer parts, lower power, fewer places where it can fail, physically smaller size. Right? So understanding these equivalences of these mathematical equations corresponds to equivalences of circuitry.
Can you try and memorize these properties?
No, you don't have to memorize them. Some of them will be things that you use so often that they'll become second nature. On my exams, I let you have pages of notes, and so you can always put these down on a note sheet. And really, we don't use them that much unless, you know, it's an exercise of, you know, transform this equation into another. But in practice, the ones that we use the most become pretty much second nature, like, you know, the fact that AB equals BA. But there is one that you might want to actually work to memorize, and that's De Morgan's theorem. And this is a good one to memorize just because it pops up so many times. It pops up all over the place in Engineering 250. It pops up in computer science. It pops up in other engineering courses. It's one of these things that applies to so many different areas in the universe that it's somehow something fundamental. And so here's what De Morgan's theorem says in Engineering 250. If we do a NOR, take A or B and complement that, that turns out to be the AND of A bar with B bar. So it lets us move between ors and ands by negating the two variables here. And similarly, if you had A ANDed with B and you negate that, so this is a NAND of AB, that turns out to be A bar ORed with B bar. Okay, those are De Morgan's theorems. And this is really important because if you want to write AB with a bar on top of it, you cannot write it like this. Right? These are not equal. In particular, A bar ANDed with B bar is actually the negation of A or B, not the negation of A and B. So these bars, whether they go across both symbols or they go across each symbol separately, you get totally different things. Okay, this actually means A bar ANDed with B bar, and it's not the same as AB with a bar on top. So these we'll encounter a lot, and we'll use them a lot. And they're pretty powerful. So we'll come back to De Morgan in a few minutes. I'll tell you why it's such a cool rule. All right, what else can we do with Boolean algebra? Well, if you have AB and you OR it with AB bar, you end up with just A. This is something called adjacency. And we're going to use this in a fundamental way probably next week. And we'll see why that is. But let's just think about this one rule. AB or AB bar is equal to A. Suppose we wanted to prove this, right? We could try to take some of these rules. We could try to take, distribution or De Morgan or some other set of rules and prove this algebraically. But again, we're in a world where we only have two possible values for any variable, which means that if we have two variables, A and B, there's only four possibilities. They're both 0, they're both 1, A is 0 and B is 1, or A is 1 and B is 0. So if we can prove that this is true in each of those four cases, we've proven this is always true. So we can do proofs by truth table. So let's see an example of this. I want to prove that this is equal to that. So I'm going to make my truth table. I'm going to list the four possible values for A and B. And I would like to write down what this is equal to in each of these cases. Okay, here's a general trick. When you're doing a question like this, work in steps. Okay, the way I'm going to show you this makes it really easy for somebody grading your paper to know exactly what you did. And if you made a mistake, to know whether it's a fundamental mistake or just a typo. Okay, so the first thing I'm going to do is I'm going to write down the value of A ANDed with B. Okay, there's really nothing I can do here except just use the truth table for an AND gate. So X and Y, here's what the AND looks like. It's 1 when both inputs are a 1. So my AND looks like this. Okay, now I want to write a column for A ANDed with B bar. Well, don't make your life too hard. Don't try to do this in your head. Let's make a separate column first for the complement of B, for B bar. So B is 0, B bar is a 1. B is 1, B bar is a 0. Okay, now if I want to write AB bar, I'm taking this column, and I'm ANDing them. Okay, 0 ANDed with 1 is 0, 0 ANDed with 0 is 0, 1 ANDed with 1 is 1, 1 ANDed with 0 is 0. Okay, now I have a column for AB, and I have a column for AB bar. I can OR two columns together, right? That's not too bad. So let's write a column for AB or AB bar. And I'm just going to use this column and this column and AND them. That's going to give me this column. Sorry, OR them. Plus sign. Okay, 0 ORed with 0 is 0. 0 ORed with 0 is 0. 0 ORed with 1 is 1. 1 ORed with 0 is 1. Okay, now I have a column that hopefully without any mistakes shows me the value of AB or AB bar. And all I have to do is observe that in every possibility for whatever values A and B have, this expression has the same value as A, right? 0 and 0, 0 and 0, 1 and 1, 1 and 1. Since in all possible cases this expression has the same truth value as A, that allows me to say that they're equal. So we've proven that this statement is true, this theorem, and we did it by using a truth table. And you can always do that, right? Unless the question says don't use a truth table. But in practice, you can always prove things that are true by just writing out all the possible values of the inputs and showing that the left side and the right side are always the same. This is something that's really easy for computers to do, right? If you want to prove theorems on a computer and you can break them down into this Boolean domain, computers have no problem doing this. It might take a long time, but it's a very straightforward thing to set up. Not so straightforward for people. All right, so any questions about that? All right, so you can look in the book. You can find other expressions, but the basic ones. Is that a question?
I'm curious, how did you decide what the values for A and B were?
Let's see.
So A was 0, 0, 1, 1, B was 0, 1, 0, 1.
Oh, so I've got 4 cases here, right? One possibility is that A is 0 and B is 0. I don't know if that's true, but it's a possibility, right? It could also be that A is 0 and B is 1, or A is 1 and B is 0, or A is 1 and B is 1. So I don't know what the values of A and B are, but I know that exactly one of these 4 cases applies.
Gotcha, that makes sense.
Okay, cool. And this stuff ties into logic, right? This was where this stuff came from. This was in the 1850s that people, George Boole was working on this stuff, because we can use this for logic, right? So as you want to know a statement about, if it is raining or if today is Thursday, then such and such. Well, maybe it's raining, maybe it's not. Maybe it's Thursday, maybe it's not. But there's only 4 possibilities, right? It's raining and it's Thursday, it's not raining and it's Thursday, it's raining and it's not Thursday, or it's not raining and it's not Thursday. Don't ask me to repeat that. Right? So this was developed to understand, human thought, to understand how humans reason, how our brains process logical arguments, and to try to put that on a mathematical footing. When we started developing artificial computers in the 20s, right, this was a branch of mathematics, a language that was right there and was useful for codifying some of what we were trying to do.
That seems like such an abstract thing to study without computers.
That's what mathematicians do, actually. I mean, I agree, it is very abstract. But people were interested in philosophy and logic thousands of years ago, right? Trying to understand how people think and trying to understand what is logical and what isn't. Aristotle and all of these people, right? This has been studied for a long time, and to put that on a mathematical foundation, which is, you know, what Boolean algebra was developed for. Yeah, it's pretty radical, the things that people have done. So, so here's an AND operation. This is kind of a sidebar I'm going to do here, and then we're going to take a few minutes break, and then we'll come back and talk about more circuitry. But here's an AND gate, right? AB. Here's a NAND gate. All right, what happens if I do the following? If I feed A into both inputs of a NAND gate, I get A ANDed with A negated. Okay, well, one of the theorems that I didn't give you, one set of theorems is, for example, A ANDed with A is just equal to A. A ORed with A is just equal to A. And you can get that from the truth tables, right? If X is equal to Y, 0 ANDed with 0 is 0, 1 ANDed with 1 is 1. 0 ORed with 0 is 0, 1 ORed with 1 is 1. So ANDing something with itself just gives you back that something. ORing something with itself just gives you back the something. So if I take A and I AND it with itself, I just get A. So A NANDed with itself is just the inverse of A. Which means that if I have a NAND gate, I could take A and B, I could NAND it with itself, and then I could feed that into both inputs of another NAND gate, and I would get the complement of my input, which was AB bar, so I get AB double bar, which is just AB. So I can make an AND gate out of two NAND gates, which is kind of cool. We also know that AB bar is equal to A bar or B bar. And we know that A or B bar is equal to A bar ANDed with B bar. Well, if I negate both sides of this, I get this equation, and the double negation of A or B is just A or B. And so if I take A and negate it, and I take B and negate it, and I take the NAND of those, I get an OR gate. Well, I can negate something by just feeding it into both inputs of a NAND gate. So I can take A, put it into two inputs of a NAND, take B, put it into both inputs of a NAND. That gives me these two. Take the result of those, put those into the two inputs of a NAND. I've got myself an OR gate. And if I run that through two inputs of a NAND, I would get myself a NOR gate. So it turns out if all I have is a NAND gate, I can make all my other gates out of that. And it also turns out if all I have is a NOR gate, I can make all my inputs out of that. So these things are called computationally complete gates, right? If in your parts bin in the collaboratorium you didn't have all those chips that you had, all you had was a NOR gate, you could still build all the circuits you needed. It would take a lot more work and a lot more wire, but you could still do it. All right, so let's go ahead and take about a 4 or 5 minute break, and we'll come back and then we'll start putting together some circuits along the lines of what you're going to do in your traffic controller. All right, so come back in about 5 minutes. All right, so just to kind of give you an example that's kind of interesting, let me show you a circuit. This is a pretty complex looking logic diagram. If you zoom in and you look at this, what do you notice about it? What's something that jumps out about this? What kind of...
There's very many different inputs
There's very many different inputs. What kind of gates do we see?
and outputs.
They're all NAND gates, right? Or NOR?
They're all NOR gates, right? Each of these symbols here, this is an OR with a bubble on the output, this is a NOR gate. The entire circuit is made out of NOR gates, right? Why in the heck would you do that? Build a whole circuit out of NOR gates. Well, if you go up to the very top, and this is a fuzzy scan, but if you look here at the date where this was approved, it's 1966, okay? And this was part of the Logic Flow module from the Manned Spacecraft Center in Houston, Texas. This was part of the computer that went onto the Apollo missions that eventually went to the moon. And this was designed in the mid-60s. Well, in the mid-60s, there were no parts bins in the Collaboratorium with 74 LS04s. There were no integrated circuits that you could commercially buy. So NASA hired a team at MIT to design logic gates and build these control modules. And the question up front was, how many different kinds of logic gates do we need? Well, here's a 2-input gate, here's a 3-input gate, right? Today, we get a 2-input gate, or we get a 3-input gate, or a 4-input, right? But since none of these gates existed at the time, they all had to be manufactured. And they were going to be manufactured and used in a low-pressure environment, a vacuum. They were going to be subjected to G-forces when they launched. There were going to be temperature extremes and so on and so forth. And all that stuff has to be tested thoroughly. And if any of this fails, right, human lives are on the line. So the decision was made, it's going to be most effective to design a single kind of gate and to just use it, right, again and again. So they designed a NOR gate and they simply used it in whatever ways they needed. So if you needed an AND, you would use De Morgan's law to turn your NOR gate into an AND. And so you find, you know, page after page of circuits like this that you know, are just made out of one type of gate. So it really is something that, you know, gets used sometimes. And this happens today in modern electronics. A lot of the devices that we build on top of now only have a single type of gate inside. And if you want to use a different kind of gate, you fake it, right? You trick that gate into working like a different kind of gate. So this stuff is not just theoretical, although a lot of it feels pretty theoretical at times. All right, so let's talk about how we go from an idea to an actual circuit. So let's say we want to build a combination lock. We're going to build a circuit that has 3 buttons on it, and if you put in the right magic combination of button presses, we want our lock to open. Okay, that's our goal for the next few minutes. We're going to make a combination lock with 3 inputs. Okay, so I've described it to you. That would hopefully be put in writing to whoever was going to design this. But here's the first thing that they would probably come up with: a system diagram. So let's make a system diagram for our combination lock. So it's going to look like this. It's going to have 3 inputs, which I'm going to label A, B, and C, and it's going to have an output which I'm going to label L. This is our lock output. Okay, at this level, the system diagram, I'm not going to describe AND gates and OR gates and truth tables. I'm just looking at kind of what we call a black box view. What are the inputs? What are the outputs? Okay, and as part of this, I need to specify what the heck is A, B, C, and L. What are those things? Okay, so A, B, C are button inputs. Those are the things that the person using this can press. And L is the lock output. Okay, sometimes when you press a button, it generates a logic 1 signal. Sometimes when you press a button, it generates a logic 0 signal. Most of the circuits we wire up in this course, when you press a button, you would get a 0 out, not a 1. So I need to specify what the values of A, B, and C mean. So I'm going to say 1 equals pressed, 0 equals released. Okay, the lock signal output, should that be a 1 when it's locked or a 1 when it's unlocked? It's totally up to the designer. You know, you might want to make it so that a 1 means it's locked and a 0 means it's unlocked. But if you do that and the power fails, your system's going to unlock, because a power fail, your output voltage is going to be 0. So if you want it to be locked in the event of a power fail, you might want a 0 to mean locked. Okay? Well, I'm going to let 0 be unlocked, so if the power goes off, this will open up. So I'm going to say 1 equals locked, 0 equals unlocked. All right, you gotta have the system diagram specified. For me, for you, for the person who's using this, for the person who's checking it and testing it and so on, these have got to be specified up front. And if you don't do this, there's a good chance you get partway through your project and it's late at night and your brain switches and you start thinking, oh, a 0 is when the button's released, a 1 is when it's pressed, right? And now you're heading down a path where there's just going to be lots of confusion. So always draw a system diagram, label your inputs and outputs, describe what they are, and list what the 1s and 0s mean. Okay? So do that for experiment 4 on lab 1 also. Okay, you've got car sensors, you've got lights, green and red. Make sure you indicate what the 1s and 0s mean for each of those. Okay, the next step is to make a truth table. So a truth table comes from understanding what this system is supposed to do. So let me write a truth table for this lock. So we know that there's 3 inputs, A, B, and C. So I'll list those up here. And we know there's one output, L. So I'll list that as an output. And I'm going to list all possible combinations of A, B, and C. And that's it. There's only 8 possibilities. All right. I am going to change this around. I'm going to say 0 is unlocked, 0 is locked, and 1 is unlocked. Okay? So I'm changing what the 0s and 1s mean. We'll do it the other way another day. Okay, so 0 is locked, 1 is unlocked. Okay, we need a secret combination that we're going to code into the circuit that will unlock the system. So somebody give me your favorite 3-bit secret code. First one who speaks up gets to name it. Anybody give me a 3-bit number?
101.
Perfect, thank you. All right, so our secret unlock code is 101. So to unlock, we want a 1. So we're going to put a 1 right there. And for any other combination, we're going to have a 0. All right. So this is what we want. Let me show you a slightly easier version of this system. Suppose somebody had said, let's unlock the door when the combination 111 is put in. Okay? Then we would want to unlock in this case and stay locked in all these other cases. Okay, so in that case, this would be the truth table for our circuit. and we would have to write an equation for L in terms of A, B, and C that generates this truth table. Does anybody have any idea what such an equation might be?
ABC.
A, B, C. This is the truth table for a 3-input AND gate. The output is 1 if A is 1 and B is 1 and C is 1. Otherwise, the output is 0. So if we happen to want to build a circuit that generates a 1 when both A, B, and C are, all of A, B, and C are 1, there's the equation, and we're done. Well, that's not exactly what we've got, okay? But why does this work? Because this says if A is 1 and B is 1 and C is 1, set the output to 1. Okay, well, we've got something almost as simple as that. We still have 7 zeros and a single 1, but look where this 1 is. It's sitting here on the 6th row. And in this row, what's the case? A equals 1 and B equals 0 and C equals 1. It's still an AND of 3 things. But in this truth table, A had to be 1 and B had to be 1 and C had to be 1. In our actual circuit, A wants to be 1 and B wants to be 0 and C wants to be 1. Well, we don't have an AND operator that tells us when the first thing is 1 and the second thing is 0 and the third thing is 1. But let me rewrite this slightly differently. How about this? A equals 1 and B bar equals 1 and C equals 1. Does everybody see that this is the same thing as that? Right? Because if B is 0, then the complement of B is 1.
So it's another version of saying B naught.
So it's another version of saying B naught, exactly. So while I know how to write an equation that tells me if 3 things are all 1, it's just an AND. So if I were to AND A with B bar and C, this should be 1 when A is 1 and B bar is 1 and C is 1, which is also the case when A is 1 and B is 0 and C is 1. So if I set L equal to A, B bar, C, this is exactly the truth table I get. Okay, this is a really powerful trick we can use again and again to write equations corresponding to truth tables. Now suppose our truth table looked a little different. Suppose we had A, B, C, and L. And this time, let's suppose that we wanted to unlock, in this case up here, where A is 0 and B is 1 and C is 0. Could we write an equation for that?
Yeah.
Yeah. So we want L to be 1 when what happens? A is 0 and B is 1 and C is 0, which is the same.
B, C naught?
Mm-hmm, exactly. So we want A bar to be 1, we want B to be 1, and we want C bar to be 1. And so we just want the AND of these 3 things, A bar ANDed with B, ANDed with C bar. So over here, the equation was L equals A, B bar, C. In this case, the equation is L equals A bar, B, C bar. So for any truth table where we have a single 1, we can write a simple AND expression where we might have, you know, A or we might have A bar. But we can cobble together a single AND expression that gives us this exact truth table. So we're making progress now. So let's make it a little more challenging. Because, you know, this is the combination to your secret cookie jar or something. and you don't want to give this out to too many people, but you trust the person you live with the combination, so you want to give them access to the secret cookie jar also, but you don't want to give them your combination, because if you kick them out, they would have your combination. They could come back and eat cookies, right? So we want two combinations that unlock this circuit. So we want a truth table like this, so that if you put in the combination 1, 0, 1, that generates the unlock signal, but also if you put in 0, 1, 0, that generates the unlock signal too. Well,
like an OR gate.
So this is exactly what an OR gate is for, right? We know that if we do A ANDed with B bar ANDed with C, that will output a 1 if ABC is 1, 0, 1. And we know that if we do A bar ANDed with B ANDed with C bar, that will output a 1 if ABC is 0, 1, 0. And now we want L equal 1 when A equals 0 and B equals 1 and C equals 0, or A equals 1 and B equals 0 and C equals 1. And so L should be 1 when this is true or this is true, so we OR them together. And there's an equation for our locking circuit. All right, so that's sufficient for you to be able to write a truth table for your traffic intersection for experiment 4. You're not required to come up with an equation for it for this lab, okay? But the next lab, lab 2, you will be coming up with an equation and a circuit, okay? So this is how you can come up with an equation from a truth table, and this is what we're going to talk about all next week, is going from truth tables to equations. But this is the basic gist of it, right? Every time that there's a 1, we can write an expression which is true in that particular row of the truth table. And if we have multiple things that we want to cause the output to be a 1, we can just OR them together. All right, making sense? So let's go on to circuit design. So suppose we're doing this. We've got a task to build a circuit that unlocks with these two particular combinations of inputs. We've drawn the system diagram to show A, B, C, and L. We've drawn the truth table, and now we've written an equation. The next step is to build a circuit. The next step would be to simplify this if we could. We're not going to worry about simplifying for now. So we're going to build an equation that implements, we're going to build a circuit that implements this equation. Okay, so our equation is L equals A bar B C bar, or A B bar C. Okay, here's what you could do, but don't do this. You can just start building, right? Here's A, and let's put it through an inverter to get A bar. And let's take A bar and B and C and put C through an inverter. And let's AND those. And then let's take A itself and let's take B and put that through an inverter. And let's take C and let's put that through an AND gate. And then let's take that and this and put that through an OR gate, and there's L. Okay. Yeah, that works. Technically, it's correct. It's kind of sloppy, right? And if this is a much more complex equation, this grows in a really kind of organic way. So let me show you a really, really systematic way to draw a circuit corresponding to any equation like this. And it's nice because it's really clean, it's easy to follow, and it's also easy to change. Okay, and it will actually be something that we build on in a couple of weeks when we talk about programmable logic. So this is a way that, you know, we might sketch a circuit, but let me show you a systematic way to do this. So we're going to use the same equation. So we're going to do L equals A bar B C bar or A B bar C. Okay, we've got a system diagram. We know we have three inputs A, B, C. I'm going to take each of those inputs and I'm going to run them vertically on a piece of paper. So like this. And I'm going to leave some space in between them. And next to each of these, I'm going to pull off this signal and run it through an inverter. And take the output of that inverter and run that vertically as well. Alright, and I'm just going to label these down here for my own reference. This is now A bar, B bar, C bar. Alright, I need an AND gate with three inputs. So let me draw an AND gate over here with three inputs. And what do I want the inputs to be? A bar, B, and C bar. So I'm going to run a horizontal line from this first input over to A bar. And I'll put a little dot here to indicate a connection. And I want my second input to come from B, while B is this vertical line right here. So I'll run a horizontal line to B. And my third input comes from C bar, that's this sixth vertical line. So I'll run a wire over to there. And this is an AND gate, and I can label my output A bar, B, C bar. And my other AND gate should be generating A, B bar, C, so I'll run one input to A, another input to B bar, another input to C, and this is A, B bar, C. And now I can take these and I can put them into an OR gate, and there's my signal L. And this is a fair bit cleaner, it's easier to follow, and as you're building your circuit, you know, if you want to use a highlighter to trace your wires, this makes it easier to do that.
Wouldn't there be a power supply in this? I mean, I kind of remember something about a power supply in 120.
Definitely. So when you work with logic diagrams, right, we're not worried about power. We have these bare wires that just, we assume there's logic ones or zeros, and this is just a symbol that takes three ones and generates a one, otherwise it generates a zero. But when we're actually building circuits with chips, we have to supply power to the chips. So we'll come back to that diagram in a second, but let's look at a chip. So up here we wanted to take our signal A and invert it. Well, we would get a physical chip, which looks like this, and it's a 74LS04. And if you go to the website, and you come down under component specifications, and if it asks you for a password, just put in Clark. We can look at a hex inverter, 74LS04. We can find the data sheet for it. So 74LS04 is this package up here, and I've drawn it sideways, but the little notch is at the top up here. On my paper it's on the side, and it tells us that if we send an input into pin 1, we can read the inverse of that from pin 2. Okay, pin 1 is labeled 1A, pin 2 is labeled 1Y, and there's a picture here which says 1A goes into an inverter, 1Y comes out. So pin 1 goes through an inverter to pin 2. And similarly, pin 3 goes to 4, pin 5 goes to 6. So I can think of this picture like this. Alright, but pin 7, that's labeled ground. And pin 14 is labeled VCC. That's 5 volts. So if we were actually building this circuit, we need to connect this pin 1 to our ground line. We need to connect pin 14 to 5 volts. Right? And that's what activates or powers the circuitry inside this device to let it do logic operations. So this is a logic diagram. But after we finish a logic diagram, then we extend it to create what's called a wiring diagram. And a wiring diagram actually shows how you would physically connect chips together to get your desired circuit. So here's a typical thing that we would see in a wiring diagram. We would see what's called a component ID block. So up here in the upper right corner, and eventually this is what you'll be doing in some of the later labs, we have a block labeled component ID block. And ignore my extra stuff here. So it would say component, and we would say where do we connect VCC, where do we connect ground, and maybe where do we have no connections. And every time that we have a logic gate in here, we map it to some component up here. So for an inverter, we want a 74 LSO4. Well, we don't want to write 74 LSO4 over and over and over again, so we just name this something. For example, U1, U1, U1. And we have a column up here, which is, I don't know, I'll just call it ID or something. Okay, so in this table, I would make an entry for U1. And I would say U1 is a 74 LSO4. And on this chip, VCC comes from pin 14 and ground comes from pin 7. And which pins do I connect to? Well, here I want input A to go into the input of an inverter. I have 6 inverters in here. Okay, so I'm just going to pick this first inverter. I'm going to say let's feed A into pin 1. So I'm going to put a little 1 up here. And if I'm feeding into pin 1, the inverted output comes from pin 2. So this is going to be pin 2. And for B, maybe I'll go into pin 3 and I'll come out on 4. And for C, I'll go into pin 5 and I'll come out on 6. And if I had more inversion that I wanted to do, I could use these pins as well, because these look like this. Right? There's a total of 6 inverters in here. Well, I'm only using these 3 inverters, so 8, 9, 10, 11, 12, and 13 I've not used. So I would list those up here in this component ID block as no connection, NC. So 8 through 13 is no connection. And then my OR gate, I would find what part number that was. I would figure out what the number was. I would call this something like, you know, U2. Yeah, let's just go ahead and do that one. So hex OR gate is a 74 LS32. And if I look at that, 7 is ground, 14 is VCC. This is often the case, but not always. Okay. A lot of the chips we use in the beginning of the course, ground will go to pin 7, power will go to 14, but that'll change eventually. So this is a 74 LS32. And I don't know, I can pick any of these gates that I want. Let's just pick this upper left one. Let's feed in on pins 13 and 12 and come out on pin 11. So I could say this input's going to be 13. And this will be 12, and this will be 11. And then I don't have any connection to 10, 9, 8, or 1 through 6. So I could say no collection on 1 through 6, and 8 through 10. And then you do the same thing for your AND gates. And when you're done, you have a complete wiring diagram. Okay? It's a diagram that means you never have to look at your data sheets again. You basically pull these components out from your parts bin, you plug them into your proto board, you connect ground to here, power to there, and then you just start running wires. I need a wire from pin 2 on chip U1 to pin whatever this is on chip whatever that is, right? Probably U3. And it gives you a very systematic way to build your circuit, and if your circuit doesn't work, it gives you a systematic way to debug it. Now, debugging in this class is not going to be the same because we're going to be working on a simulator, Tinkercad, to build our circuits and to test them. So we can't really talk about how you would use a multimeter to trace your way through your circuit as easily, but we'll dabble with some of that later. But this is your wiring diagram, okay? And the other point of a wiring diagram is you can hand this to somebody who doesn't know anything about Engineering 250. Who knows nothing about digital logic, truth tables, none of that stuff, and they can build your circuit from this. Because it's just follow the instructions. Find this chip, plug it into your proto board, take a wire from pin 13, connect it to whatever pin this is on that chip, and so on. Right? And so your wiring diagram is probably the ultimate output of your whole design process. And you know, back here on the Apollo guidance computer, right, these chips had part numbers associated with them. They had their inputs and outputs labeled, right? And it was always the same chip, so you knew where to put power and ground. But this is how you wire the board up, right? And it gets approved by somebody who reviews it, right, and signs off on it. Right, and so this is yeah, so it's drawn by this person, it's checked by this person, and then it's approved by 2 people, right? Which means they can send this design off, this wiring diagram off to somebody, to a lab somewhere, to actually assemble it. So there's this whole sequence of steps, right? Starting with what is the problem we're trying to solve, what's the system diagram look like. I guess it's worth writing these down. So there's the problem, there's the system diagram, there's the truth table, there's the equations, there's the logic diagram, and then there's the wiring diagram. And then there's the actual circuit board. If you were physically building this, you would actually pull out the parts and put it together. And then there's the testing. And once the testing is approved and it passes all the tests, you're done. You're ready to ship to your customer or demonstrate to your teacher or whatever. So we're going to spend a lot of time looking at this question of going from equations to logic diagrams. Sorry, from truth tables to equations. We've seen one way to do it. That's a way called a product of sums representation. We're going to see other ways to do that, including things to simplify. So once you come up with your equations, sometimes there's an extra step in here which is to simplify them. And we'll spend some time talking about how to do that, which is going to be using something called K-maps. Okay, so it's just previews of where we're going. All right, let me talk about inputs and outputs, because we have, you know, this mystical A here. For a logic diagram, A, B, C, L, those are great. For a wiring diagram, we don't expect a technician to find a letter A and solder it to a wire going into input 1 of chip U1, right? We need something here that actually corresponds to electrical components. So we want to talk about how to generate input values A, B, and C, and also how to read output values like L. Okay, so this is the last topic for today, input and output. So inputs and outputs. Okay, on the output side, output's a little bit easier, right? We have some kind of circuit and it's generating, you know, some signal L. We know it's a 1 or a 0. Typically what we want to do, we want to hook it up to a light, an LED. Okay, if you use these in 120. Basically an LED is a little tiny device. It has 2 inputs to it, and if you run current through it, it lights up. Okay, the symbol for an LED is this. I usually draw a circle around it. And if you run current through it, it turns on. It glows red or green or whatever color the LED is. So typically we take this end and we connect it to ground. And there's a symbol for ground. The trick with LEDs is if you run too much current through this, it destroys the device. It makes a little popping sound, it smells bad, and then it doesn't light up anymore. And this thing doesn't have any resistance by itself. So suppose you have 5 volts coming out here, and you connect this to ground. How much current do you get flowing through that wire? Any guesses?
Would it be 5?
How would you get 5?
To be honest, it was just a wild guess.
It's not a bad guess. So we know Ohm's law, V equals I times R, right? So voltage is current times resistance. Well, what's the resistance of a wire, theoretically?
Not really sure, to be honest.
Do wires have a lot of resistance or a little resistance, you think?
Little resistance.
Very little resistance, right? A resistor, right, which is designed to cut down current, has a lot of resistance. A wire has very low resistance. A perfect wire has resistance of 0. So if we have 5 volts and we divide it by the resistance, we should get the current. Well, if we have 5 volts divided by 0, what's 5 divided by 0? I won't tell your math teacher.
Undefined.
Yeah, it's undefined, but it's something really, really big. Basically, the smaller this thing gets, the bigger 5 over 0 gets. Right? 5 over 1 is 5. 5 over 0.1 is 50. 5 over 0.01 is 500. You can see where this is going. If I do 5 over 0, I'm going to get like a gazillion or something, right? What we would call infinity. So if you have a wire connecting 5 volts to ground, you get theoretically infinite current, which is definitely more current than an LED can handle. So we put a resistor in here, typically a 1 kilo ohm. And that just cuts down the amount of current going through the LED. So that's the output side, very straightforward. Just take your output and connect a 1K resistor, connect an LED, and put the other end on ground. And now if I have a logic 1 coming out of here, 5 volts, this will light up, and it will have about 5 divided by 1,000 amps, which is about 5 milliamps. And that's a good amount of current for an LED. And if this is a logic 0, I have 0 volts here, 0 volts here, no current, the LED is off. So this is an easy way to examine an output. Attach this to an output, and if the logic signal is 1, the LED lights up. If it's 0, it doesn't light up. And you can do that in Tinkercad. Alright, the input side is a little more confusing, but if we do it like this, it will always work. Let's say we have a circuit and we want to feed in either 5 volts or 0 volts. Okay, the switches we have are typically something like this. We can make a connection or we can break a connection. And we might try to do something like this. And now, yeah, if we close this switch, we get 5 volts going into the input. But the problem is, if we open the switch, the input's not connected to anything. And that's not the same as getting a logic 0. Okay, this is really important. A disconnected input is not the same as an input connected to 0 volts. A disconnected input is basically undefined. So here's how we can use this simple switch to feed in a 1 or a 0. Take the signal that you want to generate, connect it up through a 1 kilo ohm resistor to 5 volts, and then also connect that input signal to a switch, which can be used to connect to ground. Okay, if your switch is open, which is, where it's not making contact, this is not part of the circuit. Your input goes through a resistor to 5 volts. Your input is equal to a logic 1, 5 volts. If your switch is closed, meaning it looks like that, now this input goes directly to ground. It also goes through a resistor to 5 volts, but the direct path is to ground. Your input will be a logic 0, which is 0 volts. So this is how we feed inputs to circuits. We take the input, we run it through a resistor to 5 volts, and then we use a switch to optionally pull that input to ground. And if I press this switch so that it's closed, I get a 0. If I release the switch so it's open, I get a 1. Okay, so that's how we generate inputs and read outputs to and from circuits. And we'll review this again, okay, once we actually start implementing circuits in Tinkercad. But if you want, you can try building up this circuit and you can see what it does. You can also build up your circuit using an LED for an output. And I think in Tinkercad, maybe, you have to try this, if you do this without a resistor in here, I think it'll show you a symbol like the LED blew up. So you can experiment with that. It's like an Easter egg. All right, that's it for our time today. So I have office hours tomorrow morning at 8. And if you're stuck on questions or something, you can shoot me an email. And remember, next Tuesday, we have a new Zoom code, so announcements should be going out shortly. That'll have the new link to follow to class. All right, have a great day, everybody, and I will see you next time.